So here is a plot similar to the Keeling plot, but for methane, and you can see that methane also has this annual cycle. Mostly comes from agriculture. Rice paddies, for example, emit a lot of methane. Cattle, as we said, and also wetlands, so they can have a seasonal cycle as well. So that's pretty cute. And you have this black line, which is the annual mean. And you can see that sometimes it has flattened, not always well explained, but nonetheless, in just the last 40 years, it has gone from less than 1650 ppb as opposed to ppm. CO2 is in parts per million by volume, whereas methane and N2O are in parts per billion. Okay. Much smaller, but nonetheless, as we saw, their global warming potential is very high compared to CO2. So that's CO2 increasing, and here is a longer term view of N2O increases in the atmosphere. Again, in parts per billion, 1 order of magnitude smaller than methane, but the greenhouse warming potential is 1 order of magnitude higher. So you compensate there, right? So you can see that there has been an exponential increase in N2O since the Industrial Revolution, especially in the beginning of the 20th century. Okay, again, not good news. Even in the ice cores, there is N2O records, but the uncertainty tends to be high for different gases from the paleo records, as we will see a little bit later on. Okay, so one thing I should make clear, when we talked about greenhouse warming potential, we didn't say the time period. So typically they are measured over 100 years. If you have concentration of various greenhouse gases as opposed to CO2, what is their greenhouse warming potential? So methane, carbon dioxide is 1 again by definition. Methane is 23 over a 100-year period. Nitrous oxide almost 300. HFCs, which I had mentioned, based on the various factors, can be 10,000 to 12,000 times the carbon dioxide. Okay, that's massive. Perfluorocarbons, more than 5,500. Sulfur hexafluoride, another industrial product, can be 22,000, more than 22,000 times CO2 in terms of greenhouse warming potential over a century. Obviously, concentration is not the only thing. Lifetime in the atmosphere, the other critical factor that matters. At the carbon dioxide can be 5 to 200 years, depending on how quickly it gets taken up and buried or hangs around in the atmosphere. Methane, much shorter, only about a decade. Methane is highly oxidizable, very quickly gets oxidized in the atmosphere to produce carbon monoxide and water vapor, and then carbon monoxide goes into carbon dioxide. So it just moves into carbon dioxide, doesn't disappear from the system. Nonetheless, methane itself has residence time of about a decade. Nitrous oxide is more than a century. So if it is 300 times more global warming potential and 115 years of residence time, you can imagine that it being 1 order of magnitude less than methane is not a big comfort, especially considering that it has been increasing exponentially through the 20th century. Hydrofluorocarbons hang around for a couple of centuries. Again, HFCs, replacement for CFC was a good idea, but turned out to be a bad idea for global warming, especially considering its global warming potential. And similarly for perfluorocarbons and sulfur hexafluoride can stick around for a couple of thousand years. This one more than 3 millennia. We put it into the atmosphere, it stays around for 3 millennia. That is not a joke, folks. We are affecting many generations down the line. So even if you're having doubts about global warming in your lifetime, You have to remember that if you are married and if you're a person who is produced children and is waiting for grandchildren or planning to produce children and looking forward to playing with the grandchildren, then you better worry about the environment you're going to leave for them, right? So percentage of emissions in 2000 in CO2 equivalent, 77% is carbon dioxide, 14 is methane, and so on down to a small percentage for perfluorides and sulfur hexafluoride and so on. So at least try to carry forward the important concept that greenhouse gases, molecular structure is important, their concentration is important, but their residence time and their global warming potential together determine how harmful they are to the environment in terms of causing global warming. Important concepts.